Welcome! In this session, we'll explore LeetCode problem number 1343, number of subarrays of size k and average greater than or equal to threshold. This is an interesting problem that challenges us to work with subarrays and thresholds, applying our skills in array manipulation and mathematical reasoning. Let's dive in and break it down together step by step. In this problem, we are tasked with finding the number of subarrays of a given size k within an integer array ARR such that the average of the elements in each subarray is greater than or equal to a specified threshold. The input consists of the array ARR, an integer k representing the size of the subarray, and another integer threshold. The output will be a single integer indicating the count of such subarrays that meet the condition. For example, if the input array is 2, 1, 3, 4, 1, 2, 5, 6, with k equals 3 and threshold equals 4, we need to analyze all possible subarrays of size 3 and determine how many of them have an average greater than or equal to 4. For the given example, the subarrays of size k equals 3 are 2, 1, 3, 1, 3, 4, 3, 4, 1, 4, 1, 2, 1, 2, 5, and 2, 5, 6. Calculating the averages, we find that most of these subarrays have averages below the threshold of 4. However, the subarray 2, 5, 6 has an average of 4.33, which meets the condition. In total, there are 3 subarrays that satisfy the requirement, so the output for this example is 3. This process demonstrates the need to systematically evaluate all subarrays of size k and check their averages against the threshold. Now, consider another example where ARR equals 1, 2, 3, 4, 5, k equals 1, and threshold equals 3. For this case, since the subarray size is just 1, each element of the array is treated as a subarray. The values are 1, 2, 3, 4, and 5. Among these, the elements 3, 4, and 5 have averages that are greater than or equal to the threshold of 3. This gives us a total count of 3 subarrays that satisfy the condition. The output for this example is also 3. This illustrates that when k equals 1, the problem simplifies to counting the elements in the array that are greater than or equal to the threshold. To solve this problem efficiently, we need to consider various constraints and edge cases. The constraints specify that the array length can go up to 100,000, and each element can have a value up to 10,000. Additionally, the size of the subarray, k, can range from 1 to the length of the array, and the threshold can range from 0 to 10,000. Key edge cases include scenarios where the array has only one element, where the array is at its maximum size filled with the largest possible values, and where the threshold is at its extremes. To handle these efficiently, we can use a sliding window approach to calculate the sum of each subarray in linear time. Instead of calculating averages directly, we compare the sum of elements in each subarray to k** threshold to avoid unnecessary floating point computations. This approach ensures the solution remains scalable and efficient even for the largest input sizes. To solve the problem of finding the number of subarrays of size k with an average greater than or equal to the threshold, we first considered a brute force approach. The intuition behind this method is straightforward. We iterate through all possible subarrays of size k within the given array. For each subarray, we calculate its sum, divide by k to obtain the average, and then check whether this average meets or exceeds the threshold. If it does, we increment our count of valid subarrays. This approach is simple, but when you look at its complexity, you'll see it's not efficient for large arrays. The time complexity is O(n*k), as we need to compute the sum for each subarray of size k, and with larger inputs, this quickly becomes computationally expensive. However, it does have a space complexity of O(1), as we're not using any additional data structures beyond the variables needed for the computation. While the brute force approach is conceptually simple, it has significant drawbacks. It's inefficient for large arrays because we repeatedly calculate the sum of overlapping subarrays. These redundant calculations waste computational resources, making the approach impractical for larger inputs. To address these inefficiencies, we turn to the sliding window technique. The sliding window approach optimizes the process by maintaining a running sum of the current subarray of size k. Instead of recalculating the sum from scratch for each subarray, we update the sum incrementally. Specifically, as we slide the window forward, we subtract the element that is leaving the window and add the new element that's entering. This way, we avoid redundant computations. Once we have the updated sum, we check whether it divided by k meets or exceeds the threshold. If it does, we increment the count of valid subarrays. This optimization reduces the time complexity to O(n), as each element is processed exactly once, while still maintaining a space complexity of O(1). The sliding window approach offers clear advantages over brute force. It's significantly faster because it avoids redundant calculations and reuses the sum of overlapping subarrays. This makes it particularly effective for large inputs. One key observation that simplifies the implementation even further is that, instead of dividing the sum by k to calculate the average, we can directly compare the sum to the product of the threshold and k. This eliminates unnecessary division operations, which can save time. Additionally, by maintaining the sliding window of size k, we ensure that the computation for overlapping subarrays is minimal. The aha moment here is realizing that this technique balances efficiency with simplicity, making it the ideal choice. The sliding window approach not only reduces the time complexity from O(n*k) to O(n), but it also uses constant space, ensuring scalability and ease of implementation. When comparing the two approaches, there are clear trade-offs. The brute force method is easy to understand and implement, but it's computationally expensive and impractical for large inputs. On the other hand, the sliding window approach, while slightly more complex to implement, offers significant performance improvements. It minimizes redundant calculations, scales well with larger arrays, and strikes a balance between efficiency and simplicity. Given the problem constraints and the need for scalability, the sliding window technique is the optimal solution. Its ability to reduce time complexity to O(n), while maintaining constant space usage makes it far superior for this task. To solve this problem, we need to determine how many contiguous subarrays of size k have an average greater than or equal to the given threshold. Since calculating averages repeatedly can be computationally expensive, we reformulate the condition to work with sums. Specifically, we calculate the target sum, which is k multiplied by the threshold. Any subarray of size k with a sum greater than or equal to this target sum satisfies the condition. To achieve this efficiently, we use the sliding window technique. This method allows us to calculate the sum of each subarray in constant time after the first one, making the overall time complexity linear with respect to the size of the array. We start by initializing our variables, a counter to track valid subarrays, the target sum to avoid repeated calculations, and a variable to store the sum of the current window as we process the array. The first step in the algorithm is to compute the sum of the initial window, which consists of the first k elements of the array. This sum is stored in the window_sum variable. If this sum is greater than or equal to the target sum, we increment our count of valid subarrays. Next, we slide the window across the array. For each step, the window shifts forward by one element. To update the window_sum efficiently, we add the next element in the array and subtract the first element of the previous window. This ensures that the window always reflects the sum of exactly k elements. After updating the window_sum, we check if it meets or exceeds the target sum. If it does, we increment the count. Once we've processed the entire array, the count variable will hold the total number of valid subarrays, which we then return. This approach is highly efficient because it avoids recalculating the sum for each subarray from scratch. After computing the initial window sum, the algorithm simply updates the sum in constant time for each step. By processing the array in a single pass, we achieve an overall time complexity of O(n). Additionally, by working directly with sums rather than averages, we avoid floating point arithmetic. This not only reduces unnecessary calculations but also minimizes potential precision errors. There are a few edge cases to consider. If the array has fewer than k elements, there are no valid subarrays, so the result is 0. If the threshold is 0, any subarray of size k will meet the condition as long as the array contains non-negative numbers. Negative numbers in the array are also supported, as the condition remains valid for any threshold value. The algorithm uses minimal extra space, relying only on a few integer variables, making it both time and space efficient. The algorithm's implementation in Python is straightforward and adheres closely to the step-by-step process we've outlined. We define a function that takes the array, k, and threshold as inputs. First, we calculate the target sum by multiplying k with the threshold. We initialize the count variable to 0 and compute the sum of the first k elements to establish the initial window. If this sum meets or exceeds the target sum, we increment the count. Then, we loop through the remainder of the array, updating the window sum by adding the next element and removing the first element of the previous window. At each step, we check if the current window sum is valid and, if so, increase the count. Finally, the function returns the total count, which represents the number of subarrays that satisfy the condition. Analyzing the algorithm, the time complexity is O, n. Computing the initial window sum requires O, k operations, and sliding the window across the rest of the array involves O, n, k steps, each of which takes constant time. Combined, this results in a linear time complexity. The space complexity is O, 1, because we use only a few integer variables and no additional data structures. To illustrate the process, consider an example where the input array is 2, 1, 3, 4, 5, 8, 2, 3, k is 3, and the threshold is 4. The target sum is 12. Starting with the initial window, 2, 1, 3, the sum is 6, which is less than 12. As we slide the window, we update the sum and check if it meets the target. For instance, when the window becomes 3, 4, 5, the sum is 12, which is valid, so we increment the count. This process continues until the entire array is processed. In the final steps of the example, the sliding window moves to 8, 2, 3, where the sum is 13, also valid, bringing the total count of valid subarrays to 4. This efficient approach highlights the power of the sliding window technique. It eliminates the need for redundant calculations, making it suitable for handling large arrays with up to 100,000 elements. By focusing on sums instead of averages and using minimal additional space, the algorithm achieves both simplicity and optimal performance. This makes it a robust solution for scenarios where performance is critical, such as processing large datasets or real-time applications. This solution implements the sliding window technique to efficiently count subarrays of size k with an average greater than or equal to the threshold. First, the minimum sum required for a valid average is calculated as k** threshold. This ensures that we can directly compare subarray sums to this value without needing to calculate averages repeatedly. Next, the sum of the first k elements is calculated and stored in window_sum. This represents the sum of the first window. If window_sum is greater than or equal to min_sum, the count of valid subarrays is increment. The loop then slides the window across the array. For each step, the window sum is updated by subtracting the element that is leaving the window, error, at k, and adding the new element entering the window, error, I. This ensures that the sum is adjusted in O(1) time without recomputation. After updating the window sum, the code checks if the new window meets the condition. If it does, the count is increment. The approach is efficient, with a time complexity of O(n), where n is the length of the array, since each element is added and subtracted from the window sum exactly once. This is a significant improvement over a brute force approach, which would require recalculating the sum for every potential subarray. The function finally returns the count of valid subarrays, which is the solution to the problem. Here, we start by defining the number of subarrays method, which takes three parameters: the integer array ARR, the size of each subarray k, and the threshold that the average needs to meet or exceed. The first step is to calculate the minimum sum required for the average to meet the threshold, which is done by multiplying k with the given threshold value. Then, we initialize a variable window sum to store the sum of the first k elements of the array. This is achieved using a simple loop that iterates k times, incrementally adding each of the first k elements to window sum. After this, we declare a count variable that will track the number of valid subarrays. We then check if the initial window sum is greater than or equal to the calculated minimum sum, and if so, we increment the count by 1. Now, we begin sliding the window across the rest of the array by iterating from index k to the end of the array. For each step, we update the window sum by subtracting the element that is sliding out of the window and adding the new element that is sliding in. After updating the window sum, we check if the current window sum meets or exceeds the min sum. If it does, we increment the count variable. This process continues for every valid position of the sliding window until we reach the end of the array. Finally, after the loop completes, we return the count, which represents the total number of subarrays of size k whose average is greater than or equal to the given threshold. This implementation efficiently calculates the result in O(n) time complexity by leveraging the sliding window technique, ensuring we only traverse the array once and avoid unnecessary recalculations. In this first example, we are tasked with finding subarrays of size 3 whose average is greater than or equal to 3. To achieve this, we start by calculating the minimum sum required for a valid subarray. Since the threshold is 3 and the subarray size is 3, the minimum sum is 3 multiplied by 3, which equals 9. Next, we calculate the sum of the first subarray, 1, 2, 3, giving us a window sum of 6. At this point, our count of valid subarrays is initialized to 0. Now, we check the first window, and since the window sum of 6 is less than the minimum sum of 9, the count remains unchanged. We then slide the window to the next subarray, 2, 3, 4. To update the window sum efficiently, we subtract the first element of the previous window, 1, and add the new element, 4. This gives us a new window sum of 9, which meets the condition of being greater than or equal to the minimum sum. Therefore, we increment the count to 1. Now we slide the window once again to the next subarray, 3, 4, 5. Using the same approach, we subtract the first element of the previous window, which is 2, and add the new element, 5. This gives us an updated window sum of 12. Since 12 is greater than or equal to the minimum sum of 9, we increment the count to 2. At this point, we have reached the end of the array, and the total number of valid subarrays is 2. In the second example, the array is 1, 1, 1, 1, 1, with subarrays of size 2 and a threshold of 3. The minimum sum required for a valid subarray is 2 multiplied by 3, which equals 6. The sum of the first subarray, 1, 1, is 2, and the count is initialized to 0. Since the window sum of 2 is less than the minimum sum of 6, the count remains unchanged. Sliding the window to the next subarray, 1, 1, we update the window sum by subtracting the first element of the previous window, 1, and adding the new element, 1. The new window sum remains 2, which is still less than the required minimum sum. As we continue sliding the window across the array, the sum of each subarray remains 2, which is consistently less than the minimum sum. No valid subarrays are found, so the count remains 0. The total number of valid subarrays in this case is 0. In the third example, the array is 5, 5, 5, 5, 5, with subarrays of size 3 and a threshold of 5. The minimum sum required for a valid subarray is 3 multiplied by 5, which equals 15. The sum of the first subarray, 5, 5, 5, is exactly 15, so we increment the count to 1. Sliding the window to the next subarray, 5, 5, 5, we update the window sum by subtracting the first element of the previous window, which is 5, and adding the new element, also 5. This keeps the window sum at 15, which meets the condition, so we increment the count to 2. We continue sliding the window to the last subarray, 5, 5, 5. Each time, the window sum remains 15, which is greater than or equal to the minimum sum of 15. For each valid subarray, we increment the count. By the end, we have found 3 valid subarrays in total. This example demonstrates a case where all subarrays meet the condition, resulting in a final count of 3 valid subarrays. Here, we break down the time complexity of the solution step by step. First, the initialization of the min_sum value involves a simple calculation, which is an O(1) operation because it doesn't depend on the size of the array. Next, to compute the sum of the first k elements using sum arr k, we need to traverse these k elements once, making this step O(k). After that, the sliding window iteration begins. For every index from k to n, arr 1, the loop iterates nk times, where n is the length of the array. Within each iteration, the sliding window sum is updated in constant time by adding the incoming element and subtracting the outgoing one, which is an O(1) operation. Additionally, checking the condition window_sum equals min_sum is also done in constant time. Combining all these steps, the iteration phase requires O(nk) time in total. Adding up all contributions to the total time complexity, we have O(1) for calculating min_sum, O(k) for the initial sum computation, and O(nk) for the sliding window iteration. Since k is fixed relative to n in this problem, it doesn't grow with the size of the input array. As a result, the dominant term is O and K, which simplifies to O, N, when considering big O notation.
Now let's discuss the space complexity.
The algorithm uses only a constant number of variables, such as min_sum, window_sum, and count, all of which take O1 space. Furthermore, there are no additional data structures involved, no auxiliary arrays or copies of the input are created. The algorithm directly operates on the input array ARR, so the space complexity is O1. This minimal space usage solidifies the space complexity at O1. To better understand the efficiency of the sliding window approach, let's compare it to the brute force method. A naive solution would involve generating all possible subarrays of size k and calculating their averages. For an array of length n, there would be approximately O, n, k plus 1 subarrays, and computing the sum of each subarray would take O, k time. This results in a total time complexity of O, n asterisk k. In contrast, the sliding window approach eliminates redundant calculations by reusing the sum from the previous window, reducing the time complexity to O, n. The space complexity remains O1 in both cases, but the optimized time complexity makes the sliding window approach significantly more efficient for larger arrays. Now let's examine the best, average, and worst-case scenarios for the algorithm. In the best case, even if all subarrays satisfy the condition, the algorithm still needs to process the entire array, so the time complexity remains O(n). In the average case, regardless of how many valid subarrays are found, the algorithm iterates through the array only once, so the time complexity is still O(n). Finally, in the worst case, the algorithm again processes the entire array, maintaining the same O(n) complexity. To mathematically confirm the big O analysis, the initial sum computation takes O, k, and the sliding window updates take O, n, k. Ignoring constants and lower order terms, the total time complexity is O, n. Since the algorithm only uses a constant amount of memory, the space complexity is O1. This demonstrates that the solution is both time and space optimal for this problem.
When solving this problem, there are several common mistakes that can trip you up. First, an incorrect sliding window implementation is a frequent issue. If you forget to subtract the element that's leaving the window when updating the sum, the result will be an incorrect calculation for the current window, which can lead to wrong answers. Another mistake involves off-by-one errors in indexing. For example, miscalculating the starting or ending index of subarrays is easy to do, especially when dealing with the first or last window. This can lead to missing valid subarrays or accessing out-of-bound indices, which might even cause runtime crashes. Finally, be cautious about floating point precision issues. Relying on floating point division to calculate the average can introduce subtle bugs due to precision errors. Instead, use integer comparisons, like checking if the sum is greater than or equal to k asterisk threshold, to avoid these pitfalls entirely. Now, let's look at a couple more common mistakes. Misunderstanding input constraints can be problematic. For instance, assuming that k can be larger than n, the length of the array, or overlooking edge cases like k = n can lead to unnecessary checks or incorrect assumptions in your code. This not only wastes time during implementation but can also result in bugs. Another frequent misstep is relying on brute force for large inputs. While a brute force approach with O(n)² complexity might work for small arrays, it becomes impractical for larger test cases, often resulting in time limit exceeded errors. Recognizing when to shift to an optimized approach is critical for both performance and correctness. This problem is a perfect example of why the sliding window pattern is so valuable, and it's often tested in interviews. Understanding and explaining why sliding window is more efficient than brute force is a key skill. Along with that, avoid using floating point operations unless absolutely necessary, as integer comparisons make your code cleaner and help you avoid precision issues. Interviewers are also likely to test your solution with edge cases, such as when k equals the length of the array, k = 1, or when the threshold is at its minimum or maximum possible value. Always verify that your solution handles these scenarios correctly. Finally, adopt an optimization mindset. After initially describing the brute force solution, proactively suggest and implement the optimized sliding window technique to showcase your problem-solving abilities. If you're preparing for interviews, it's helpful to explore related problems that use similar techniques.
For instance, LeetCode 209, minimum size subarray sum, is another sliding window problem, but it focuses on finding the smallest subarray that meets a certain condition. LeetCode 643, maximum average subarray I, is very similar to this problem, as it also involves finding the maximum average for a fixed subarray size. LeetCode 1004, max consecutive ones 3, uses the sliding window approach to maximize consecutive ones by flipping zeros. Lastly, LeetCode 424, longest repeating character replacement, applies sliding windows in the context of character frequency analysis. Practicing these related problems will help you solidify your understanding of the sliding window technique and see how it can be adapted to different scenarios. To wrap up, there are several approaches you can take to solve this problem, each with its own trade-offs. The brute force method, which has n² complexity, involves iterating through all possible subarrays of size k, computing their sums, and checking if their average meets the threshold. While this is simple to implement and easy to understand, it's inefficient for large inputs. A more efficient option is the prefix sum technique. By pre-computing prefix sums for the array, you can calculate subarray sums in constant time. This reduces redundant computations but requires extra space to store the prefix sum array. The most efficient approach is the sliding window method, which maintains a running sum of the current window of size k and updates it in constant time as the window slides. This solution is optimal in terms of both time and space but requires careful handling of edge cases to ensure correctness. Great job! We've successfully analyzed and solved LeetCode problem number 1343 using an optimized sliding window approach. Remember the importance of choosing the right algorithm based on problem constraints, and keep practicing related problems to strengthen your skills. Thank you for joining, and don't forget to like and subscribe for more coding tips and tutorials. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!